Welcome to our Nano Day celebration at the Nanoscale Research Facility at the University of Florida. My name is Gary Scheifele, and I'm going to take you through what we can do with our X-ray tomography, specifically on our X-ray microscope, our Zeiss versus 620. So as we go through the overview, this is something that I use for training, but we can go into more detail. What I'm doing in the next hour or so is going to be something that can easily be covered in a couple semesters worth of courses. So there are digital downloads available from our university library, and I'm sure that many other universities have similar downloads. These are more for clinical applications. However, the basic principles apply throughout, whether I'm scanning rocks or metal castings or people. When we talk about X-ray tomography, we first think about what specimen that we want to use and what we want to learn from it. After we've thought about that, we then, based on what we know about X-ray production and X-ray detection and what we have to do to reconstruct, then we will decide how to place it in the X-ray beam and maybe how to prepare it such that we get that right placement as centered as possible or as easily with the least amount of artifacts in the final package. So we're going to talk about how we're producing X-rays, and we're going to talk about how we detect X-rays. Then we'll talk a little bit about reconstruction and a little bit about post-processing. And of course, we're going to generate huge data sets in the 2 to 30 gigabyte or even larger size range. So we've got to think about what we're going to save and where. So the basic CT process starts with an X-ray tube. It could be a beam line. So if we're doing this at state-of-the-art, we're going to go to Brookhaven or CERN or something where we have tomography as an experiment station on the beam line. But using something like a simple X-ray filament-based X-ray tube, or in the Zeiss, I don't have diagrams of that, but they use a Lab 6 filament on the source that we're working with. But what we're doing is we're going to have some source of electrons. So in our other CT, we have a filament. We adjust the filament with current and potential to a point where we can extract electrons. Then we use accelerating voltage and extraction grid to then direct the electrons towards our target. So this is acceleration potential, and all the electrons are going to have the same kinetic energy once they pass that anode. We're going to use magnetic lenses to focus that beam on a target, and it's not going to be like light. It's going to be more of a spiral, but we're going to hit that target, and the target is where we're going to generate X-rays. The X-rays are going to go in 360 degrees, but we're going to collimate that so that we end up getting a cone-shaped beam, a lot like a flashlight beam with a LED source. And we're going to illuminate a specimen with that. Now, the specimen is going to attenuate X-rays, which means that it's going to cast a shadow on the detector. So I'm going to have more photons hitting here and less in the middle. And we do have issues with the flat panel detector that this is a longer distance than it is at the middle. So we're going to have less intensity at the edges than we do at the middle. Increasing the current on the filament will increase the number of electrons and then thus the number of X-rays. So we have little less of a shadow. And then increasing the voltage on the anode plate due to the Edison effect will increase both the number and penetrating power of the X-rays. so much less of a shadow now. During the scan, we're going to rotate the sample 360 degrees and collect projections or 2D X-ray images during that rotation. In cross-section, some of these sources will look like this. Now, again, this is not what's on the Zeiss, but just in general, if I've got a filament-based machine, this is all under a very high vacuum. We want to keep that electron beam from scattering on any air molecules. We also don't want it to short to ground. So basically the whole case is ground. I don't want it shorting. It could short back to the grid cap, could short back to the receptacle. We're trying to minimize shorting. So any of these instruments are going to have a tube conditioning process after it's been off for a while to make sure that we can have a stable beam without shorts. In a transmission tube, the target's usually a few microns coatings of tungsten on diamond or molybdenum or beryllium on beryllium. The lateral limits can be as small as about a half a micron. In the Zeiss, we can have very small angles. So in effect, the beam becomes more coherent, and we can do some phase contrast work. But in some cases, these are user maintainable with training. In the Zeiss, that's a closed source. We can't open it up. Okay, attenuation. How do we get grayscales? So we have a material, we have a detector. The detector normally consists of two layers. The first layer is a scintillator. The second layer is, say, an amorphous silicon or a CCD or a CMOS detector. In the Zeiss, these two layers are separated by some distance. There's a scintillating layer, and then there's the detection layer. And that's where we're getting some magnification off the objectives. What's a scintillator? Basically, it's a chemical that will take an X-ray and then re-emit a visible light photon. And that photon is something that the silicon-based detector can see. So we have energy coming in. We have our object casting a shadow. Where it's widest, it's going to cast the deepest shadow. If I increase the atomic number or the packing factor of that element, then it's going to cast a deeper shadow, and it gives us more attenuation for a variety of factors we'll get to in a little bit. If I've got a longer sample, same material, it's got more attenuation. It's a linear attenuation coefficient. In the Zeiss, so I've got a dual stage optical architecture. So I can move my sample back and forth between, and in fact, the sample stays in one place, rotating around a fairly small, I can offset this by a little bit. But in the Zeiss, what happens is I can move my detector either far back or very close. I can move my source either far back or very close. That gives me a range of geometric magnifications. So A plus B over A is my geometric magnification. And then I have optical magnification from my scintillator and the size of the scintillator to my camera, which is back here. And between my detectors and my camera, I actually have a physical shutter. Now, in an SEM, resolution is driven by the size of the beam and the beam interaction volume. So we can get down to maybe a couple nanometers in an SEM, lateral resolution, gold on carbon, something like that. In CT, in X-ray CT, what we're doing is basically dividing that shadow that's cast on a grid by the number of pixels that it's going over. So if I've got a specimen 12 millimeters in diameter, and it casts a shadow of 2 by 2 cells, so I have 12 divided by 2 cells, or 6 millimeter resolution. If I back it up some more, now it's going to cast a wider shadow. So 12 millimeter diameter by 6 cells is 2 millimeter resolution. If I back it up even further, and now it goes across 12 by 12 cells, I get 1 millimeter resolution, and I can actually see some of the happy face, of course, if it's turned 90 degrees from that direction. So closer to the X-ray source, I get higher magnification, higher resolution. But if I've got too big of a sample, I can't do the entire sample at that resolution. I'd have to move it out farther. And that's sometimes an advantage because maybe that larger sample doesn't have as fine of features as my smaller sample does. And I can put a lot more energy through the system at a higher magnification. Why can I do that? Well, we'll talk about geometric unsharpness in a minute. Anytime that we're doing CT, we always have to think about what our required resolution really has to be. Does Mario just need to have, do we just need to know that Mario's got blue dungarees, or do we need to know that he's got blue eyes? This sort of scan is probably going to take 2, 3, 4 times as long as the low resolution scan does. All right, we've talked about grayscale, origins of grayscales. Now let's talk about what we can do to have different grayscale graduations associated with different materials. If I've got too much penetrating power in the system, in effect, everything washes out. I get very little contrast in low density areas, and I have very little, not even that much contrast in high density areas. If I have too low a penetrating power or too low of a kV, all the X-rays are stopped by the object. I lose resolvability in the high density areas. What we'd like to do is set up our 2D projections such that the ratio between the high transmission areas, say here, and the low density areas are in the 2 to 20 range. So if I divide my high energy, say that's 10,000, and this is at 2,000, so I've divided that, so I've got a ratio of 5. I'd like it to be in this 2 to 20 range, which translates to 5 to 50% transmission. We'll hit on that again later. Contrast resolution really depends on the range that of grayscales that the detector can measure. And on the Zeiss, it's actually 1 to 65,000, 8-bit gray. Here we're doing 10,000 X-ray events per unit time. And on the Zeiss, that's 65,000 for whichever detector, even the flat panel works that way. But I have got a certain amount of energy coming in. I've got a certain amount of energy coming out. Lower counts are going to be to the left-hand side of the histogram. Higher counts will be to the right-hand side. So we have air on the right side, sample on the left-hand side. We want to make sure that these numbers are high enough. So in the Zeiss, that's shooting for about 5,000 counts out of 65,000, that we can be sure that we're getting enough real signal through the detector from the source. What step size resolution that we can get here really depends on the detector dynamics. That can be the digital resolution, the analog to digital conversion, and the overall noise of the electronics. All right, noisiness. So if I'm not getting enough photons through, I'm going to have a noisy scan. Noisy scans relate to noisy reconstructions, and noisy reconstructions means that I might be taking 5 times as long to segment something, and that is your word of the day, segment. Now, if I want to segment something that's really noisy, I have 3D pathways of grayscale values that basically merge. So instead of doing everything automatically with clear definitions, I'm doing things with manually by basically drawing in 3D. The other problem with a noisy scan is that I lose detail for small features. So I've got the same size little void here in this volume as I do over here. And because of the signal noise passing through and something called Compton scattering, the signal above noise here is much lower than the signal noise here. So just realize that the smaller the features and the more the less differential between the surroundings and that feature, the cleaner your scan has to be, the less grainy. All right, let's talk a little bit about geometric unsharpness. And although Zeiss minimizes this, it doesn't completely overrule it. So there are tables on the side of our instrument that tell you what resolution that you can get to with a certain detector and a certain binning on that detector. Don't go outside of those ranges or you will be encountering this geometric unsharpness. What this is illustrated by if I've got more or less a point source and I've got rays coming from that. So now a ray can go across an edge, whether it's external or internal in the instrument, and then that falls on a pixel element or two at the most on the detector, so the edges appear to be sharp. Well, if I turn up the power, so that could be higher kV, could be higher current, I'm putting more electrons on a certain spot, and if I keep that spot size the same, I'll probably be burning through the target. So I don't want to do that, and thus usually when we're going to higher energies, we're getting a bigger spot size. The problem with that now is that we're getting rays from either side of the spot, and when those rays end up crossing the edges internal or external of the sample, they fall over a wide range of pixels, and that means that the edges appear to be blurry. And again, that makes it really hard to segment anything later. So higher power, larger focal spot, more geometric unsharpness. We can use that power level, but we have to have the sample farther away or at a lower resolution. Now, those same rays from either side of that spot fall within a pixel or so, and the edges appear to be sharp again. Higher magnification, more geometric unsharpness. In general, the Versa 620 spot size is in the 4 to 8 micron range for flat panel use. For other applications, for the other objectives, go with the tables. But from what Zeiss tells me, if I go to, say, the 40x objective, and I'm trying to get to the limit of what it can do, which is about 300 nanometer voxel size, then I may want to use not the full power that the kV setting can use, can be set to, but maybe a third of it. 2/3 of it. We also want to remember the distance square law. And this is very important in the Versa. We can get the same magnification in the Versa with many different source object detector combinations. In general, to make faster scans, we want that source to detector and detector to object, source to object and object to detector distances to be as short as possible. Again, what we're doing is anytime we double the distance, we're quartering the intensity. So instead of having something take 1 second, now we double the distance and we're getting something that takes 4 seconds to acquire. Anytime that we're scanning, we're going to be trading off between resolution, speed, and signal to noise. Sometimes we're going to go pure speed. Sometimes we're going to try to do as best as we can on resolution. But our parameters are going to be kV, power, filtering, averaging, magnification, and detector capture time. So let's talk about the X-rays that we're getting off of our tube for a moment, because this is important when we're thinking about how it's going to interact with our sample. Simple X-ray tube, again, we've got our filament, got an electron beam, in a microfocus or D-tube or a deflection tube, that's going to hit a much more heavily coated post that might be actively cooled, might be rotating, but we're going to have X-rays coming off from the side. And then again, for transmission, got a thin layer of target material on a window, and we've got X-rays coming straight through. This is what we're going to try to use for anything that we've got that we need to do true grayscale analysis. It's not going to be as good as a medical CT, because in a medical CT, we're only going to have a few widths of pixels in the middle, and those are going to rotate around. But in this one, it's going to be worse because my energy spectrum of this side is not going to be the same as this side. I'm going to have less X-rays, but more energetic and overall, and then more X-rays, but on average, less energetic on this side. So how do we make the X-rays? So, I'm not going to cover filament saturation right now. That's with the filament instruments. But we're going to generate X-rays either by Bremsung or deceleration radiation. That's where the electrons coming in are slowed and emit. And since I've got to conserve energy, I'm going to emit a photon of the difference. And if it's basically being stopped by the nucleus, then I'm going to emit the highest energy X-ray. 99% of the kinetic energy is converted to heat and visible light, and of that 1% converted to X-rays, not all are going to be particularly useful. The other X-rays that we're going to get are from electrons being kicked out of core shells and higher valence electrons falling in and emitting characteristic X-rays. So this is going to happen, and it's a useful parameter as well. For example, I'd really rather not get below about 60 kV on a tungsten source, because I'm going to drop about half of my counts doing that. I might get a little bit better contrast going to 50 kV, but I'm not going to get nearly as good of count rate. And in many situations that we deal with, soft samples, biological samples, doubling a scan time allows the sample to shrink or sag, and now I'm getting useless results even if I get slightly better contrast. The main factor here is that this is a polychromatic spectrum. Unlike at a national lab beamline where they can filter and get almost monochromatic X-rays, we don't have enough. And we're always going to be working in these sorts of systems with the polychromatic X-ray spectrum. If we change the tube current and keep the boundary energy the same, the X-ray output is proportional to the current. So every time we double the current, we double the total number of photons. However, notice that the mean energy is less than the boundary energy. So I'm looking at like 40 kV of the average energy, and the mode is much less than the boundary energy. So maybe my peak in energy is at 30 kV, where my boundary energy is at 100. Sometimes we can use this to our advantage versus a national lab. Sometimes it's a major limitation. Changing the tube high voltage, keeping the current the same, now the X-ray output is proportional to the current, to the potential squared, and not only to the tube power. Again, Edison effect. So anytime we increase that boundary energy, we're going to increase at the same overall current, we're going to drastically increase the amount of electrons being produced and thus X-rays. So we have said that we have a polychromatic spectrum, and sometimes it's useful and sometimes it's not. So when it's not useful, we may want to filter our energy spectrum. In this case, we're going to use something. This might be a little bit of aluminum, might be some copper for, stuff in the 180 to 120 range of kVs. If I'm doing something with concrete with steel reinforcing, I may be up in the 200 kV range. And in this case, now I want to filter more substantially. I might use half millimeter coppers. I might have half millimeter tin. In the Zeiss, they have proprietary filters, which are, I think, metal doped glasses, and they have low energy filters and high energy filters. But they're doing the exact same thing as we see here. I just don't know exactly what the reduction is where. The material will self-filter. So assume that this is the aluminum casting. This was a slide that GE/Waygate supplied in our training for our other instrument. And this is after reconstruction. So after reconstruction, our air is black and our densest parts of our material are white. Well, in this case, it's just an aluminum casting. It should all be the same level of gray within, limits for porosity and things like that. If I do a line profile across this, really, instead of doing what we see here, where it goes to a peak and then goes down, it should just be going up, straight over, and down. It's not doing that because the material is self-filtering. The low energy photons are absorbed or attenuated more substantially by the material, so I see this white rim around the side. We can do some corrections for that in software called beam hardening corrections, in which case, after correction, we can have a much more uniform grayscale from the aluminum itself, and we can see our porosity much more clearly. So in almost all of our industrial CT scans, we are going to apply some sort of beam hardening correction. I don't care what material that you're working with. All right, I've said attenuation many, many times during this presentation. And my contributors to this X-ray attenuation in the range that we're looking at, which is up to 200, 300 kV, is primarily photoelectric absorption. We have some contribution to Rayleigh scattering, and we have Compton scattering, which is X-ray fluorescence, or those characteristic X-rays that are being produced by the material. In effect, and we'll talk about this more in just a second, when the X-ray is Compton scattered, it's going in some other direction, but sometimes fairly forward scattered. So we've got to, we have to realize that some of the X-rays getting to the detector are going to be from the sample, and that can cause blurring. All right, we see that the photoelectric absorption line moves to the right as we increase our atomic number of our materials. So iron is much higher than water is, but we're still looking at a substantial amount of Compton scattering even here. What I was saying about directionality is that 100 kV, we're seeing something that's almost completely, there's a little bit more forward scattering than back scattering, but it's fairly even. When you get to 200 kV, we're about 30%, well, 50% more forward scattering than we do back scattering. And then 300, what I'm told about at 9 mega electron volts, the scattering pattern goes off to the edges of the detector, you don't see it at all, which is useful. But because of this scattering effect, if I've got high density materials and low density materials, and as this object spins during the rotation, I have overlaps. So I will have what's called photon starvation, because again, it's self-filtering. I will have areas that are concave that become very hard to distinguish where an edge is. So sometimes we can overcome that by filling all the voids with something that will absorb those X-rays locally. The Compton scattered X-rays are always going to be lower intensity than the incoming radiation. But again, our detector can't tell the difference between a 20 kV photon and a 200 kV photon. It just says, I've been hit by a photon and I'm counting. All right, that is done with that presentation. And I'm just going to pull up Zeiss real quick. Do we have anybody else in the chat other than online? Other than staff?
No, it does not appear there's any questions.
Okay, that's fine. All right, so we'll go to the advanced presentation here. All right, so common target materials for X-ray CT: tungsten, copper, vanadium, chromium, molybdenum. Tungsten's the most robust. It's not going to give you the softest X-rays. If I'm doing, we do have a moly target on a beryllium backing for the other machine. Sometimes we can get better contrast there if I'm with insects, for example, or small polymers, if I'm looking at something that I want to go down to 30, 40 kV. In general, though, the lifetime on tungsten targets is going to be a lot longer. For other X-ray tubes, like for X-ray diffraction, we're using a copper target, right? And in here, we can see what the typical penetration distances for pure elements are. We can go from carbon at about 3 centimeters at 100 keV to gold at about 101 microns, okay? That's for 33% transmission. And I told you before, we can go down to maybe 5% transmission, and then we could just increase the count time. So nice thing about the Versa is that you can count for a long time and the beam will stay stable. So it is possible to look at things like microelectronics at lower KVs and still get sort of good contrast. Not perfectly, as you'll see in a minute. So we have our geometric magnification. We have I'm going to go back and go to sample size versus resolution. Okay. High resolution imaging, sample drift. Okay, so in the Versa, scans do take quite a while, all right? We're not talking about 5-minute scans here. We're talking at least a half an hour and probably an hour, sometimes 3 or 4, if we're stitching together a bunch of stuff. So I want things to be fairly stable over time. And some of this we can do by thermally equilibrating the sample. We can have the sample in a condition where it's in a environment where if it evaporates, it has water to draw from. I'm not forming condensation around the edges, but I'm also going to be looking at drift corrections because nothing's ever perfectly stable in an X-ray system. So I can have drift corrections, so I can look at a picture that I take maybe during the scan versus a picture at the end of the scan, and overlap and allow that to be shifted so that I get the best sharpness in the final analysis. Sometimes we'll do warm-ups. Usually that's first thing in the day, but it could be for any sort of sample that hasn't been shaken, like the Zeiss will give it during the scan, because it will actually jiggle a little bit during the scan type. We can use different drift corrections. We can take a bunch of them during the scan that will make the scan a little longer. Sometimes we'll turn that off just to make it a little faster, because we don't generally change the drift corrections that often. Beam hardening, we've talked about. Their correction is something that we can do in real time. I can shift the applied beam hardening correction to a few projections, or a few rows of pixels, and determine the best for that particular application. These beam hardening streaks in microelectronics are terrible, but there's not much of a way that we can get around it at one angle. If we scan at a couple different angles through my sample, then I can recombine those volumes in 3D space and take maximums, for example, and then minimize those effects. Now, the effects at the edges, that's harder to do just by doing angles. Okay. Now, low Z materials have their own challenges, because a lot of times our filtering takes out all the energy that's going to be interacting with those low atomic number materials. So here we've got a toothpick, and a toothpick with steel and 2 layers of steel, and we can't see a whole lot there. But at the top, I've got the toothpick, and I can see the toothpick very clearly. At the bottom, I wouldn't be able to see the toothpick hardly at all. And it's shown here in, same scan as last page. So this is, that is not the same. Okay, so now we've got a toothpick with 50 microns of gold. Okay, gold leaf around the toothpick. And this is the 2D projection. This is the 3D image at this line. But now at this line, I don't see any of my toothpick, because all I'm seeing is scattering from the overlap of the gold and stuff like that. So that's what I was saying very early on about what do I need to see from my sample? How do I set the sample up so that I maximize what I need to see and minimize what I don't, or whatever interaction. So if I've got high density areas, or I've got a metal wrapped something, maybe I have to take the metal wrap off. Maybe I just use lower energy photons and just count for a really long time to be able to see this stuff inside. In this system, we can look at high aspect ratio stuff. So if I've got something like a circuit board or a thin sheet of something that I want to see the interior structure on and minimize the time that it takes, I can generate what this high aspect ratio tomography window around this is centered at the long edge. Okay, so non-heart 2-hour scan, I've got a lot of streaky artifacts. Heart with the 2-hour scan, I get almost perfectly clear tomography, something that I would see in a much longer time with a full 360. Most of the other instruments don't have something like this, just because they go a lot faster than the Zeiss does on normal stuff. But that's okay. There's advantages on the Zeiss that I can't get with my other instruments. Okay, I'm going to go back to phase contrast. So phase contrast is something that if I've got low intensity, low attenuation materials around voids and things like that. Now, with an absorption scan, I don't get a lot of contrast at those edges. Again, I'm getting, even with something like polyethylene, I'm going to get some Compton scattering there. It's going to make it hard to see that edge when I've got air versus polyethylene, when it's small enough, right? But if I've got my system set up that I've got very low cone angles, so instead of having a cone angle out like 25, 30 degrees, I have a 1.2 degree cone angle. Now I'm going to get a phase contrast signal across those edges. So I'll have a black line and a white line, which again sometimes makes it hard to do some automatic segmentation on that. But as a first step, actually seeing stuff, it makes life wonderful. These detectors are optimized around this useful energy band for phase contrast, and refraction is very slight, angle on the order of microradians. So on a mosquito, embedded in agar, probably could be wax, versus absorption plus phase contrast scanning, you can see how much of a difference that makes. Now, we can also stain that specimen, and we might actually get more information than this. But as a first pass, minimizing damage to the specimen, this is a good thing to do. Bubbles, we can see those fringes, and in a line profile across this, so this is the sort of signal that we see. So remember, I was showing you a line profile for beam hardening before, where it like went up, down, etc. Now they do have a phase contrast filter. We don't own it, unfortunately. Okay, and 2 voltage at 40 kV. So we're getting 40 kV. There's a lot more phase contrast than at 90 kV. And if we're doing phase contrast, so this is a presentation that we always have on this computer. You can go back to and look, because we would want to set up our R1 and R2 distances along these lines for these detectors, for 4x versus 20x detectors. So what happens if we can't scan everything that we want to see in one box? So we can do either vertical or horizontal, or vertical plus horizontal stitching in that case. So I could do scan 1, scan 2, scan 3 with some overlaps, and the machine will put everything back together again as one object. So this could be drill cores, it could be snout of an alligator, although I wouldn't do that in this machine, but even most insects, right, are fairly cylindrical. They're much longer than they are wide. So if I want the max resolution, I'm looking at the width. And if I want to get that max resolution all through the entire insect, then I could do a vertical stitch like this. Wide field mode, there are some ways of, again, doing stitching horizontally as well as vertically. And you will see that, some of because of the angles that we're taking rather than going straight through, I actually see a little bit better detail in some of these low density areas than I'm seeing in the first scan. And again, it takes a long time, but we get really good results out of that wide range. Okay, let's show some examples. So I'm going to escape out of this, and back to that. So on a semiconductor package point of view, this was something that someone shared with me, that they wanted to see what sort of circuitry I could see in this Apollo chip from the late 60s, early 70s. A lot of scatter in this. Very, I can see the substrate, and there's things that you can see very easily. But this was open. This was they had taken the packaging off of this, so I was looking at basically a bare surface here surrounded by gold wires. What was I saying about low density things versus high density things before? So if I take off this, so the only way I was able to do this, and it is a trick, and I actually have a patent on it, is by putting another material in contact with this that will absorb some of those scattered X-rays locally. So in this case, I was using something called quake gel, which is a polysiloxane that's used typically for figurines or museum specimens that in an earthquake zone, you don't want them dancing across the top of a shelf and falling off the edge. So very low extractables, and it flows. So if I put something like this in around it, air will displace over the course of about a day. And I have very, very good contact between the quake gel and my surface. So now, after doing that, I was able to see the circuitry in a couple different layers on that surface. And this is after being reoriented in 3D space so that I'm seeing that in this view. This was actually scanned at an angle, because if we'd scanned it flat, well, I've got a longer beam path through the material. I don't want that. And it would give me what's called Feldkamp artifacts at the top and the bottom of the sample. It works a lot better if you tilt it more than the cone angle is. Okay. Any of these regions that we have created, and let me just do this for example, I can right click and get properties. This is using a program called Volume Graphics, which is a very common industrial program for segmentation and analysis in 3D data sets. I can get, it shows me initially what my resolution was. So this was at about 1 micron resolution, almost exactly. Then I can see how many voxels there were, what the centroid of the voxels is, the total volume, the surface area. I can get a closed surface area if I do another calculation. But if we calibrate this material, we can get, well, if we calibrate our instrument, we can get true metrology out of this. Again, not that I've said it before, but in industry, the driving force for this technology is additive manufacturing. If I have a process that's taking multiple machining steps and combining them into one, I can't cut it open to find out what went wrong or what went right. I don't know that I've made a good part or a bad part until after I've done some sort of non-destructive analysis on it to make sure everything's where it's supposed to be and all the voids are open and not filled with the powder. So once I have that technology, then in academia we can use it, or in industry we can look at semiconductor packaging. I can, nope, not that. I can look at reverse manufacturing of something like earbuds. Let me minimize this. So now I've got driver and microphone assembly for an earbud. I can take off this clipping plane and see things more clearly, and I can add the case to it. So now my polymer is not easy to see, but I've got my silicone is a little bit denser than the polyethylene for the case, or the ABS maybe for the case. So I can see that a little bit more clearly. But from the scattering from all this, because I've got a magnet in there, it's basically nickel iron, it's not going to lend itself well to doing these sorts of analysis. But with some effort, I got them segmented. Now, one last thing that I'd like to point out, because we're getting down to about an hour and a half of this, and I've probably talked long enough, is that everything starts out being gray. I have a grayscale data set. And as I said earlier, it's a 16-bit grayscale data set. And this is a fairly grainy, it's not really, really clear, but I'm getting a lot of information out of it. Still, I can only see, again, depending on the psychologist that I reference, between, say, 8-bit gray or just over 100 grayscale values out to maybe 1,000. And a lot of people are in the last time I checked, were in the 400 to 600 range. That's a lot less than the 65,000 grayscale values at 16-bit gray, and we could go to 32-bit gray. The human eye is only going to see that level of differentiation with color. So if I map to color, and that is not falsely showing my data, it's maybe showing things that the human eye can't see in gray, but the computer is seeing in gray. We're just mapping colors to it so that we can more easily distinguish differences between different parts of our sample. Now, again, we have to be careful, like in all other measurements and conversions, that we do it right, but it's still a very useful tool. Okay. There are no chat questions or anything. Okay. 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 Did I want to? Okay, I'll tab. And anything else? In the Zeiss, we're doing mostly very small things on the order of a few millimeters by a few millimeters up to maybe a centimeter or so. On our other CT, we can do things much larger. So this is a violin, and I can look at clipping planes. Well, I guess I don't have that on there right now. If I do the entire neck and scroll and that, I can see the entire outside of the violin, and it should rotate for me, but it doesn't want to. I probably have a few too many things open at one time. So different clipping planes. If I go to the clipping plane, I can rotate that through, see the inside, zoom in. So we can actually see repairs that were done many, many years ago. There was a slight crack through this section that they fixed. And we can see things like wood grains, which I'm not seeing with that so much, but I can see over here. So if I click on this and come to this area, so this is a brace in between the outer edge and parts of the, okay, so now bring this over a little bit, scroll through. So one of the things that they were looking at was what type of wood was over here, and that's not the easiest way to see that. So if I can come over here, I can see this wider grain spacing. So some of it was spruce, some of it was something else. I can't remember offhand, but it was fairly easy to, willow. But again, if I've got $1 million violin or something I suspect to be $1 million violin, I don't want to have to open it up to determine whether what is or wasn't. All right. So, do you have any questions for me since you're here? No?
Nothing in particular.
Okay. So, let's see how I can end this. So, again, thank you from the